All right, so the law of conservation of momentum says in an isolated system, okay, if you've got a system where nothing else is bothering it, all right, if you have two objects, right, we add up the momentum at the start, right, of your system, it is going to be equal to the momentum at the end of your system. All right. And so that's the overall momentum. You could say it's the sum of momentums. Right. And so what it comes into play then is that let's say this guy has some momentum, right? And then all of a sudden it gets a lot more momentum. Okay. And this guy had a lot of momentum. Well, then it had to go down to a little bit of momentum so that the total momentum of the two is always the same. All right. So we could say that if these guys had the same equal amount of momentum and they're going at each other, if you add that up, your momentum might be zero if they're exactly equal momentums. All right. And so if they collide, boing, and bounce off each other, right? If their momentum at the beginning was zero, then the momentum at the end has to also be zero. Okay. And so what that says is if they bounce off each other and they go back, this momentum equals opposite of that momentum because it's zero. If the initial momentum here is opposite that momentum there, and that was zero. Okay. So back to the top. Law of conservation momentum says momentum is conserved when it's in an isolated system, when there's nothing coming in from outside. So no matter what happens in here, the total momentum in there stays the same. All right, so we have to talk about what a system means. Okay, a system for us is going to be a system or a system of objects. It's all the objects that you're watching. Joop, 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 joop. That's our system. Now we can pick one object to watch. We could watch two objects or three objects. We could pick to watch everything on the Earth and the Earth itself, right? I could watch the entire solar system. I could watch the whole universe. Okay. And it depends on what we're trying to look at. And so if we're looking at the momentum of just one object, right, we have to make sure there's no forces coming in from the outside messing it. Otherwise, our law of conservation will not work. If we got two or three objects, again, the same thing. If there's nothing from the outside affecting these guys, then we can see the conservation of momentum. So this is why sometimes you have to include the entire Earth, because the Earth can come in and affect things from the outside. All right, so our word for forces that are going on inside are called internal forces. That is like when one ball hits another, ping, 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 ping. That's an internal force because that's a force between two things that are inside our system. External forces are forces on our objects that are coming from the outside, like the force of gravity is often coming from the outside. If I had a book lying on a table, right, and I had the table here, okay, then if my system was just the book there, right, then I might have gravity from the outside, or I might have the normal force coming from the outside, right? So if I'm just looking at the book, those are two forces coming from the outside. All right, conservation of momentum. Here we go. All right, so we're going to look at a bowling ball hitting a bowling pin. So we're going to first draw our free body diagrams. There is, of course, gravity and a normal force on the ball. There is gravity and a normal force on the pin. Now we know equal and opposite forces, so there's a force going on here. So the pin is pushing that way on the ball, and the ball is pushing that way on the pin. Okay, and these two forces here and there are equal and opposite. They are an action-reaction pair. And so we see that this ball is going to accelerate to the left, and this pin is going to accelerate to the right. And the acceleration will depend on their mass, right, in addition to their force. So if we just look at the bowling pin, right, just the bowling pin, forces that are internal would be nothing, right? There's no internal forces, whatever it's holding it together, all right? If we are looking at external forces, right, all three forces, looking at the pin now, I guess the ball would be force from the ball, the gravity, the normal force, all those are external forces. Are they balanced? Well, two of them are. Okay, get down here. Gravity and the normal force are balanced. Okay. Now, if you have outside forces that are balanced, you can, if they're balanced, they have to be perfectly balanced, you can get rid of them. right? Because the net outside force then is 0. But for the pin, again, here's our pin, right? For the pin, there's still that force from the ball, okay? And so the momentum is not conserved, right? The up and down, the gravity and normal force and gravity can cancel out and still let momentum be conserved, but not in this case because there's actually this other sideways point. So then if we look at a system that's both the ball and the pin, that's kind of a pin, whatever, all right? Okay, so if we do both of those at once, are there internal forces? Well, yeah, there's the force on each other when they collide. Those are internal forces. External forces, again, would be gravity and would be the normal force. All right. Are they balanced? Well, they're balanced on the ball and they're balanced on the pin. So, yes, the external forces on each object are balanced. All right. And so then, since the outside forces are balanced, any internal forces will therefore mean things are conserved. Okay, so is this conserved? Yes. Get this right there. Yes. Yes, it is conserved. So again, the momentum of this system is conserved because there are no net outside forces. There's some outside forces, but they cancel each other, so momentum will be conserved. All right, so we can go back to stuff we know about. All right, the force of the pin on the ball and the force of the ball on the pin, those are equal, right? We know that. All right, the force of the pin on the ball or the force of the ball on the pin, right? Which one lasted longer? They lasted the same amount of time. So which one experienced a greater change in momentum, right? Remember that we talked about impulse. If I can get in here, impulse. Just today, we talked about impulse, and that is the force times time is actually going to get you a change in momentum. And so they both have the same force for the same amount of time. So the momentum change will be the same. Now magnitude, one's going to be plus, one's going to be minus. So the momentum change is the same. Okay, the change in momentum of one will be plus, and the change in momentum of the minus of the other one. And so whatever this guy gains, this guy loses. All right, for overall momentum. And so the momentum is going to stay the same. You can imagine that. If we add the two together, and if one goes up, the other goes down, the total sum will always be the same. Sort of like if I've got money, you've got money. If you give money to me, right, you've lost it, I've gained it. But the total amount of money between us does not change. All right.